Welcome back to the Deep Dive. Today we are performing some serious mechanical archaeology. We're digging into the latent space of transformers.
And our focus is on this really strange paradox.
Right, this persistent, almost structural failure of massive language models. We're talking models with 90 billion parameters.
And they can't do basic deterministic things like multi-digit arithmetic. The paper focuses on 4x4 multiplication, and they just fail.
It's a fascinating inconsistency. You see this emergent, complex reasoning on one hand, and then a total breakdown on the other.
So today's mission is all about mechanistic interpretability. We're going to contrast a catastrophically failing standard fine-tuning model, or SFT model.
With a small, just a two-layer four-head transformer. But this one was trained with something called implicit chain of thought, or ICT.
And that small model somehow achieves 100% accuracy on the task.
So the core premise setting this all up is that the standard training objective, the one that makes these big models so good at generating text.
The autoregressive loss.
Exactly. That objective fundamentally fails to induce the required long-range dependency structure you absolutely need for tracking carry operations in arithmetic.
And by reverse engineering the successful ICTO model, the researchers basically found a precise recipe for how a transformer can do it.
And this recipe has three key parts, right?
Yes. Three main findings. First, a robust way to encode that long-range dependency. Second, a very specific attention-based caching mechanism. And third, a really efficient and, frankly, beautiful underlying geometry for the digit features.
Okay, so let's start with that first part, the absolute necessity of these long-range dependencies.
Right.
When we talk about multi-digit multiplication, the real challenge isn't just, multiplying two digits together.
No, that's the easy part. The hard part is the global accumulation and propagating the carry. To predict, say, the kth digit of the product.
The model has to integrate information from all the partial products A, B, J, J, where I plus J is less than or equal to K.
And this is the crucial part. It also needs the carry, our taking from the previous column. That's the non-local part that's so hard.
So the researchers needed a way to test if the model was actually tracking this. They introduced a kind of probing signature.
Yes, this intermediate variable they call ECH, it perfectly captures that accumulated history. It's defined as the sum of all the relevant partial products for that column, plus the carry from the step before.
So if the model's hidden state actually contains a clean representation of ECH, then you know it's learned the algorithm.
Exactly. The rest is just trivial modular arithmetic. And they use this to run two really compelling tests comparing the good model and the bad one.
First up was Logit attributions.
Right. This is basically a stress test. You poke an input digit, A to roll or BJ dollars, and you measure how much it affects the final prediction for an output digit, $10.
And the results for the SFT model are? Well, they're almost blank.
It's quite striking. The attribution map shows a near total absence of dependency between early inputs and the middle output tokens.
So it's structurally blind to the cascading effect of carries. It just doesn't see it.
But the ICT model's map, it perfectly mirrors the math. The input digits A, PA, Joel strongly affect the output digits A exactly when I is greater than or equal to I plus J.
It's internally tracking how those distant inputs contribute to the final steps.
Which brings us to the most damning evidence against the SFT model.
The direct linear regression probing for ECH.
They took a lightweight probe to see if they could just decode that crucial sum directly from the hidden states of the final layer.
And this is where it really falls apart for the standard model.
Oh, completely. For the middle digits A2 through if5, where the carry math is most complex, the SFT model's hidden states just contained, well, mathematical gibberish.
What were the error numbers like?
Probing for A3, for instance, gave a mean absolute error, or MAE, of 113.27.
That's not a small error. That's catastrophic.
It's a total failure. It confirms the information just isn't there. It's not in the latent representation.
And in contrast, the little ICT model.
Extremely low MAE. For that same A3, it was down at 1.89.
Wow.
It's definitive proof. The ICT training forced the model's latent space to become this accurate, continuous, long-range accumulator. It solved the carry problem internally.
Okay, so we know the successful model did it, encoded ECH. The next question is how? How did it do this in just a two-layer architecture?
The mechanism is really elegant. It dynamically builds a kind of computational graph using its attention heads.
The paper calls it a sparse, binary tree-like directed acyclic graph, a DAG.
Right, and it's all focused on two tasks, caching and retrieval, the two layers specialized.
So layer one, what's its job?
Layer 1 is the partial product cache. Once the model has seen the full input, the layer 1 attention heads become incredibly sparse. They focus their attention on just a pair of digit tokens and on vans and a big jaw.
And they compute the product.
They compute the pairwise product, am times Schnitzel, and then embed that result into the hidden state at that specific token position. They essentially create a little memory register.
So it's pre-computing all the little multiplication steps and just storing them.
Exactly. Layer 1 makes the components. Then layer 2's job is to assemble them.
Which it does when it's time to actually predict an output digit, peak to end.
Precisely. Layer 2 attention heads then perform the retrieval and the summation. They look back at a very selective set of those earlier cache sites from layer 1.
And they pick out only the ones they need.
Only the ones relevant for that step. The ones holding the right partial products where I plus j equals k, and crucially the latent representation of the previous sum a1 to handle the carry.
They use the example of predicting 2D to last, which clarifies this perfectly.
It does. For 2 to lasers, you need 3 partial products. A to 2 $B, $A B last, and $10 B2.
And the layer 2 heads just attend to the 3 different earlier positions where layer 1 cached those specific products and then sums them up.
Yes. It's an efficient 2-step algorithm managed entirely by specializing the attention layers. This decomposition lets the shallow transformer mimic a multi-step algorithm without every token needing to look at every other token.
Which is a huge computational saving, but more importantly, it's what makes it algorithmically correct.
Exactly.
Okay, so that's the mechanism.
Yeah.
But the paper goes even deeper, from the how of the attention graph to the what of the representations themselves, the geometry of the latent space.
Right, and this is where things get really wild. Let's start with how those partial products are computed in layer 1. They use something called Minkowski sums.
A Minkowski sum. So when a layer 1 head focuses on the features for A or AJ9, its output is, what, a vector combination?
That's right. It's geometrically equivalent to a Minkowski sum, which is just a weighted vector addition, some amount of the A vector plus some amount of the B J vector. It's doing arithmetic via linear interpolation in the embedding space.
You can actually see this in the 3D PCA plots.
You really can. It's beautiful. You see these big clusters for one of the digits, say A, and then inside each of those big clusters, you see smaller nested subclusters for the other digit, BJ.
What's the proof that it's actually a Minkowski sum, though?
It's the geometric fidelity. The shape of the nested subclusters is a perfectly scaled-down version of the global shape of the Dijkstra-Dahl clusters. The covariance matrices are related by a specific scaling factor.
So it proves they're being combined arithmetically, not just mushed together.
Exactly. It's a highly efficient way to compute multiplication with simple vector math, but the structure goes even deeper than that.
To the representation of the 10 digits themselves.
Yes. The successful Icywarka model, which confirms some related work, organized its basic digit embeddings into a really surprising geometric shape.
A pentagonal prism.
Pentagonal prism. When you project the hidden states to 3D, the 10 digits land perfectly on the vertices of this shape.
How does that happen?
It's derived from the model learning to use a specific low-dimensional real Fourier basis. It picks out frequencies k equals 0, 1, 2, and 5.
That is an incredible level of self-organization. How do those frequencies create the prism shape?
So the first principal component, PC1, turns out to be the Nyquist vector. It just separates all the even digits from the odd digits.
Okay, so that's the 2 layers of the prism.
Right, and then PC2 and PC3 encode the k equals 2 Fourier pair, which arranges the 5 digits on each layer into a perfect pentagon. So you get 2 parallel pentagons stacked on top of each other.
An even pentagon and an odd pentagon.
Precisely. And this trigonometric representation is known to be algebraically optimal for things like modular arithmetic. It makes addition and multiplication very efficient. This whole beautiful geometry was completely absent in the failing SFT model.
Which brings us back full circle to the SFT failure. We have a clear diagnosis now. Standard training just doesn't organically induce this complex, specialized structure.
Not the accumulator, not the attention tree, and certainly not the optimal Fourier geometry.
And you can see this failure happening in real time if you look at the training dynamics.
Analyzing the loss and gradient norms per token is very revealing. The SFT model immediately learns the easy parts.
The simplest products, Tito's dollars and C dollars, and the very last digit, $77.
Right, their gradients vanish almost instantly. But the middle digits, C333 through 636, where all the complex carry stuff happens.
They hit a wall, an impenetrable plateau. The loss stays high, the model is trying, but it just can't converge.
It's stuck in a local optimum that can only handle the simple local parts of the problem. And crucially, just scaling up the SFT model to, say, 12 layers,
Yeah.
it doesn't fix it. It's a structural bottleneck.
So more capacity is not the answer. What
Yeah.
the model needs is a nudge, an inductive bias.
Exactly. And the solution they proposed was remarkably simple. They just added an auxiliary loss term, an MSE loss, that directly supervises the model to predict that critical intermediate sum.
So you're not just telling it the final answer is wrong, you're telling it, hey, your intermediate calculation right here is wrong.
Precisely, you're giving it a hint about the process.
And the result?
With that one change, the small two-layer model rockets to 99% accuracy. And the learning dynamics completely flip. It learns the easy digits first, sure, but then it successfully works its way inwards, solving the hard middle digits because the latent space is now forced to track.
And did it learn the same mechanism as the ICFT model?
Functionally, yes, but with a slight variation. It still uses the attention tree for caching. But one of its layer 2 heads develops this very clear, dense parallelogram pattern.
What does that mean?
It suggests it learned a slightly different but equivalent strategy. One head that efficiently attends to all the necessary inputs for a given step simultaneously, rather than having multiple heads retrieved from different cache sites. It still solves the long-range dependency problem.
Which is robust evidence that supervising the latent process is the key. That's the constraint needed to force a standard transformer to learn the right algorithmic structures.
To synthesize all this then, standard autoregressive loss just isn't the right tool for inducing the kind of non-local structured computation you need for algorithms like multiplication.
Right. The successful ICKT model gets there by specializing its layers into an attention tree for caching and retrieval.
And it builds it all on top of these very efficient algebraic representations like Minkowski sums and that Fourier basis.
And I think the most critical takeaway for anyone working in this space is that this kind of algorithmic failure isn't a capacity problem.
No, it's a learning dynamics bottleneck. And you don't solve it with massive scaling. You solve it by introducing a precise, task-specific inductive bias that forces the latent space to encode the critical intermediate steps. In this case, acyclic.
The lesson seems to be that algorithmic reasoning requires algorithmic structure inside the model.
It does. Which leads to, I think, a really significant challenge for future architectural design. If a task-specific loss based on, Fourier principles or vector sums works so incredibly well for arithmetic.
What's the more general version of that?
Exactly. What generic task-agnostic inductive biases, maybe rooted in abstract algebra or geometry, could we build into the standard transformer recipe to help it inherently learn these complex long-range dependencies for all kinds of computational tasks?